Okay, in this lecture, we will see the third problem or analysis 3. So this is the circuit now we are going to solve. So the circuit, you can look at this circuit. It's a little bit different from the previous circuits what we had seen. We had seen only the simple RC series circuit and RL series circuit. But in this circuit, you can see there are two loops. We have the voltage source, we have the resistor, and we have the capacitor. This is the loop 1. So the current I of t is flowing in this loop 1. And we have also another loop. We have one more component or the element. So that is inductor. So now this is another loop. This is a closed loop 2. So between loop 1 and loop 2, we have the common element that is nothing but the capacitor. So whenever we have this kind of different components in the circuit, you have to first write the polarity correctly. So here we have the polarity plus and minus, that is the source voltage. So the same polarity will appear across the resistor as well. So I think I missed to write that one. So I will just write here now, plus minus. Okay. So that is the polarity for the resistor, and we have the capacitor polarities plus and minus, and we have the polarity for inductor plus and minus. So here the current is flowing in the first loop is called I of t, current is flowing in the second loop is called I1 of t. Okay, so now I have to draw the same circuit in S domain, so it's very easy. So I just have to add the initial source for capacitor and inductor. Okay, so this is the voltage source. So V of t, it became capital V divided by S. R is as it is, R, and the polarity is the same, plus minus as the source voltage, plus minus, and the capacitor is the same, I write, and then here it will become 1 divided by Cs, the reciprocal of the impedance of the capacitor, 1 divided by Cs, and the initial source is like this, plus and minus, and that is V of 0 minus divided by S, that is indicating the initial source of this capacitor or the initial voltage of this capacitor. And also the same, the inductor I just draw as it is, and the polarity is the same, plus and minus. Here the impedance value is L times S, because this is inductor, so we are just writing as it is, not like here. The capacitor means the impedance is divided by 1 divided by the impedance value. So this is the for capacitor. For inductor, it's just L times S. The initial voltage I write like this, L times I of 0 minus. Remember here one major difference in this initial voltage source of the inductor. So that is the opposite polarity of the source. So here everywhere we just follow the same polarity, plus minus. We have the plus in the top, minus in the bottom, plus in the top, minus in the bottom, plus in the top, minus in the bottom. Here also plus in the top, minus in the bottom, plus minus, plus minus, plus minus. But here in the inductor, initial voltage of the inductor, the polarity is the opposite of the source voltage. So minus plus. So this you have to note down. Always it's like that. For inductor, whenever it discharge the magnetic field, whenever it collapse the electromagnetic field and the current flow occurs, that will happen the opposite direction of the source current flow. Okay, so now we can apply the KVL again. So now let us say I just write I can write the supply voltage is equal to the voltage drop occurs all the elements. I can just put plus plus plus. So for example, here I have the R times I of S plus 1 times CS I of S. So I can just write in this way, or I can also write in the other way. So for example, here I have written like this: the source voltage V divided by S, that is only the voltage is plus, everything else is minus, minus, minus. So the logic here is, so whenever we write the equation for these the voltage drop across each element, so you have to use the exit point. So for example, now I have the polarity. What is the polarity of the resistor now? The polarity of the resistor is plus and minus. So here whenever the current is coming like this, the current is coming from the source, the current is coming and then it's going through this way, entering into the positive terminal, exiting into the negative terminal, the negative polarity of the resistor. So I use this exiting polarity. So minus R times I of S. Okay. And similarly, the same current is flowing here as well, right? So here entering into the positive and exiting in the negative. So I write this minus. So minus 1 divided by CS I of S, that is the current flowing through the capacitor. And here there are two currents in this particular branch, remember. So this is the I of S is coming this way, and here we have the I1 of S is coming from the opposite way. So the current is flowing through in this particular branch is the difference between these two currents, I of S and I1 of S. So I of S minus I1 of S, that's what I have written here. Plus, and then I have to write again the initial voltage source of the capacitor, that is nothing but V of 0 minus divided by S. So here also the current is exiting, entering in plus and then exiting in minus. So I am writing the minus. So minus V of 0 minus divided by S plus V divided by S. V divided by S is nothing but the total supply voltage to this entire loop or to this entire circuit. So here, for example, the current I am writing this way, right? So here also the same logic you can apply. So the current is entering in the minus and then exiting in the plus. So I am using the exit sign. So that is the plus V divided by S here. So it's equal to 0 because we are using KVL, remember. So now I can keep this V of S in the left side and then bring everything else to the right side. So then everything will become plus. So V divided by S is equal to R times I of S plus 1 divided by CS times I of S minus I1 of S. And initial voltage, if I assume it's going to be 0, then I can just cancel this one. So that is the equation I have. This is for loop 1. Remember, this is a loop 1. Now I have to write the equation, the same equation for loop 2. So this is the final equation for loop 1. And now I have to write the equation for loop 2. So loop 2, we have only one element, that is the inductor, and we have the capacitor here. So now again I have to use the same technique. So the current is flowing in this way. So here we have it's entering in the positive and exiting in the negative. So I have to write minus sign, right? So minus LS, the impedance value, the I1 of S. Yes, that's correct. Minus LS times I1 of S. And then the same current is flowing, right? This current is just flowing like this and flowing like this in this loop. So here the current is entering in the minus and the exiting in the plus. So I have to write the plus for the initial voltage of the inductor. So plus L times I of 0 minus, and then here it's going here in this way. So here the exit sign is also plus. So plus V0 minus divided by S. And then here it's also going into this plus terminal. And here remember we have two currents. So here we have to write the current difference. So here exiting in the plus, so I am writing plus again, and then 1 divided by CS, that is the impedance of this capacitor, and then the current is two currents, right? So now I1 of S minus I of S. So here I of S minus I1 of S, here is I of S, here is I1 of S minus I of S. So this is the equation for the loop 2. So now you have written the equation for both loops. And if you assume there is no initial voltage in both capacitor and inductor, then you can ignore these two equations. You don't need to worry about this. You don't need to worry about this. So 1 divided by CS times I1 of S minus I of S is equal to, you can bring this to the right side, then is equal to LS times I1 of S. That is the equation for loop 2. So this is how you have to write the equation for given circuit by using KVL or KCL or voltage divider rule or mesh analysis or superposition theorem. So you can use whatever the analysis you can apply to the circuit, and you first write the equation either in time domain and then convert into the S domain by using the Laplace transform, or you can draw the circuit first into the S domain and then you can write the equation. So it's the same actually. So that's all about this analysis 3. So this, I just want to give you some idea how can you write the equation, how can you convert the circuit from one domain into another domain, and when you have more than one loops, how can you write the exact terms, and how can you write the polarity correctly. So always remember, when you write the polarity, so current is entering in one point and then exiting in another point of the device. So the exiting point, whatever the polarity we have, so we can write that. This is the way to write normally. But we can also use the KVL in the other way, like the source voltage is equal to, or the input voltage is equal to the output voltage. That is the basic law, right? So so here now we are putting everything in the left side instead of left and right, and then we are changing back to the left and right. So there are different ways to write the mathematical equations. I think you have studied these ideas from your network theory. I'm not going into the deep of those detail, but you have to know the basics. Now our target is how to use the Laplace transform, uh, how to convert the circuit from time domain into S domain. That's all. Thank you.